Hello everyone, so today we're going to start our first lesson of organic chemistry. So it's going to be really important that we always grab some piece of paper, a pencil, so we can practice drawing because there will be lots of drawing in this unit. But organic compounds are seen in our everyday life because they're just everywhere in the food that we eat. And it's literally just everywhere depending on what we look at. Normally, we think of the term organic means natural, such as organic fruit is grown naturally without chemicals, but that's actually not the case because in organic fruit, we actually do have chemicals within it. It's just depending on the amount. But organic compounds in chemistry is known as the study of compounds which contain at least one carbon atom. So based off of all of these examples here, we can say that we only have three that are considered organic compounds. We have B, D, and E because of the carbon atom that is found within each of these compounds. The others are not because no carbon exists. So hydrocarbons is an example that is formed from only one carbon and also hydrogen atoms. So for example, we have C3H8. And if we look at hydrocarbons, an example is an alkane, and this contains only a single bond between carbon atoms. So this is only a single bond. We can have alkenes, which contain one or more carbon-to-carbon double bond. And then we have alkynes, which contain one or more carbon-to-carbon triple bonds, okay? So we have so many different types of hydrocarbons. We're going to take a look at all three of these types throughout this unit. But you can see all the different examples here. We have a single bond, we have a double bond, and then a triple bond. And that's what makes the difference. We have alkane, which is 1, alkenes, which is 2, and alkynes, which is 3. So let's begin. We're going to start off with alkanes. So alkanes contain only a single bond between carbon atoms, and these are known as saturated hydrocarbons. And you can see here we have methane as an example, and that's the simplest form, and it is also known as a tetrahedral because of its structural shape. So this is one example in the most simplest form of an alkane. When we're looking at drawing our organic compounds, there's different ways that we can draw it. The first is a molecular formula, which shows the number of carbon and hydrogen atoms in the molecule and any other atom. We can have the structural formula, which shows all the bonds in the molecule as lines. We can have a condensed formula, which is atoms that are listed in order in which they appear in the molecule. So here in this situation, all bonds could be omitted or just the bonds between the carbons are drawn. We can have line diagrams, which use only carbon bonds. We can have a ball and stick diagram, which was seen for methane on the previous slides, where they're depicted as circles and lines as sticks. Or we can have a space-filling model, which are depicted as spheres proportional to the actual size of the atom. 5 and 6 are ball and stick, and our space-filling are only required just to identify. I'm not getting you to ever draw them. Normally in class we would have models to look at for them, but right now we're just going to be able to identify them. So we're going to look at how to draw the formulas based off of different compounds. So here we have ethane. It has 2 carbons. So you can see here we have 2 carbons and 6 hydrogen atoms. So eth here, which is a prefix for 2 carbon atoms that are bonded together. So the molecular formula would be C2H6. If we're looking at the structural formula, we have 2 carbon atoms. Remember, these are only single bonds right now. And then we have 6 hydrogen that are bonded all around our carbons. So, and they are all single bonds. So wherever there's an open space, pretty much you put a hydrogen there. But once again, we need to make sure we have 6 hydrogen forming and that obviously, we need to make sure that each of them fill structurally so that they are all stable. The condensed formula for this, if we were to write it, we're looking at it just as a whole. Okay, so we're just looking at it just as a whole. So it'd be CH3, CH3. I'm going to write it twice because there's two CH3s. If we were to draw the line diagram here, the H's are not shown, and you would literally just draw a straight line. Okay, because that is showing the carbon bonds for each. The ball and stick formula is shown as there, and then the space filling formula is shown. Once again, not asking you to draw, just asking for you to identify. Next is propane. Propane has 3 carbon and 8 hydrogen atoms, so prop is a prefix for 3 carbon atoms, once again bonded together. So we have C3H8, so we have 3 carbon bonds here, and then we have 8 hydrogen bonds all the way around our molecule. And then if we're looking at the condensed formula, once again, we're just looking at each singled. So it's CH3, CH2, okay, and then CH3. So make sure you know how it is separated. Once again, if we were to draw the line diagram, H's are not shown. We would just draw a diagram like this, where every point here, once again, is where our carbons are. We don't add the carbons, we just have to draw the lines. So we would know that all of these would be carbons, but we don't write the carbons in. Then we have our ball and stick, and then we have our space filling. Next is butane. This is 4 carbon and 10 hydrogen. But is a prefix for 4. So we have 4 carbon single bonds and 10 hydrogen. I'm not going to write all the hydrogens in, but you need to make sure that you write all the hydrogen in. And then a situation like here, we have CH3, CH2, CH2, CH3. And that's the condensed formula. If you were to draw all the H's that are, or all the line diagram when the H's are not shown, once again, we look like we're doing zigzags now because that's literally what it is. And we're showing all of the carbons. So we have 4 points here because there's 4 carbons, the ball and stick, and the space filling formula. These are all very important. I would star this page if I were you. So these are the other prefixes. So if we have pent, hex, hept, oct, non, and dec, that's depending on how many carbons. All are going to have the suffix ane, which is all single bonds. So as you can see, anes here is known as a single bond. So the general formula is C with a certain number here. H, it's going to be 2N plus 2. Okay, so once again, if we have ethane, we have 2 carbon atoms. That means the molecular formula is going to be C2H6. Okay, same thing. If we continue on, if we go to decane, which is 10 carbon, then that means our hydrogen would be 22 because it's 2 times 10 plus 2. Okay, so this is very important to remember our general formula for alkanes. Some alkanes have their carbon atoms bonded to form bonded rings, and those are called siloalkanes. So silo as a circle, cycloalkanes, same also term you can refer it to. And this is the general formula for cycloalkanes right here, so it's really important to remember it. So the most simplest structure is a cyclopropane, which is C3H6. And if we were to look at this example of it as its equilateral structure, it would be an equilateral triangle, which means the angles are all equal to 60 degrees. And if we times that by 3, we know it's 180. So therefore, it is an equilateral triangle. And that is why it's called cyclo, because it all combines together and attaches. So you have to be familiar with the following cycloalkanes here. So we have 4 different ones on this page that are going to be very important, and the following page as well. The molecular formula and the structural formula are there. There are different examples. So we have cyclopropane, that forms a triangle. We have cyclobutane, that forms a square. You can draw it out either way, but you need to know how the bondage works. So here you can see the line drawing of it, and then the molecular formula based off of the different examples. all of these are going to be very important to note. This is an activity that you can do on your own to look at the structural isomerism. Once again, we are not doing this in class because we don't have a modeling kit, but I really, really encourage you to use a link provided to build one of these if you would like, and then draw out the structural formula for both molecules. So build 2 different molecules, one that contains 5 carbon atoms and then 12 hydrogen atoms. Try 2 different structures, and it cannot be twisted into the same shape. Try that out if you would like, and if you want to send photos, you're more than welcome to do so, but I highly recommend you try that out. So, structural isomerism is really important. It is a compound with the same formula but has different arrangement of atoms and different properties. So that's why the activity prior to this is having 2 different molecules. But once again, they're different, okay? Same formula but different arrangement. So this only occurs in compounds that have 4 or more carbon atoms, because if we have less, it's too simple and we can't do that. So it has to be 4 or more. So for example here, we have C4H10. It can either be butane, which you can see there, its structural formula. And then you can also have it as 2-methylpropane, which once again, very, very similar, but it is also very different in the arrangement. So when we're looking at an example like so, they are going to have different structures, but they have very, very different properties. Okay, so so for each of these, even though it's C4H10, they're going to have different structures and different properties. So the boiling point for each of them is going to be very different. Okay, so this is known as a substitutant group, which is any atom or group that replaces a hydrogen in an organic molecule. So this is what makes it different, okay? So we have a substitutant group, so this is circled here, and that replaces a hydrogen in an organic molecule. And in this particular substitutant group is called an alkyl group, which in this situation, the prefix indicates the number of carbon atoms and the branch as YL suffix. Okay, so very, very unique. It's very important to understand that there are such things as structural isomerism, where things are different and change. And it's going to be really important that when we are naming our alkanes, we use the IUPAC rules in order to name. So this is very important. This is attached to our D2L shell, so you can take a look at it. So these are substituent groups that can happen on any different atom or group where it's going to replace a hydrogen in an organic molecule. So we have our alkyl groups. Once again, the prefix name is the same as the alkanes, but it ends in YL. So we have methyl, ethyl, propyl, isopropyl, butyl, and the secylbutyl. Once again, the isopropyl and secbutyl are going to be starred, and the reason for that is because of the line that comes off of it. Okay? The reason for that is that we can have isopropyl as propan-2-YL, or we can have secbutyl as butane-2-YL because of how we have that extra bond at the top here. So these are different examples of substituent groups. These are other substituent groups, which are our halogens. So the first were our alkyl groups. These are halogens. So we have our fluorine, chlorine, bromine, iodine. And once again, our group names are listed there. If we have our halogens, we can have alkyl halides, which are compounds which make 1 or more hydrogen atoms, and the alkanes have been replaced by our halogen atoms. So sometimes we have compounds that have normally our hydrogen atoms in the alkane, but now they're replaced by our halogen, which could be any of these 4 that are going to replace the hydrogen in the alkane group. So in these examples here, we're just going to identify the longest continuous chain of carbons based off of our information. So in this example here, identify the longest continuous chain of carbons. It can be known as the main or the parent. Remember, the parent here in this situation is going to determine the root name for the compound. So the best situation here is to take a highlighter and highlight the longest continuous chain. Remember, it has to be longest continuous, and in this situation here, it is this bottom chain that is the longest and continuous. And it's really important to take that highlighter and do so. In this example here, oops, sorry about that. When there's only one substituent, that means that the numbering is going to be really important. So the numbering of the carbon chain starts from the end of the chain, which gives the first branch, which is our substituent. And then we have the lowest possible number position. So that first branch is going to help determine the lowest possible number, and then the numbering can begin from any end. So normally we look at where this branch is, which you can see here, this is a branch, and we usually go based off of the lowest, where it's closest to, and that's where we give it. So it's closest to the left here, so that means we're going to label this as 1, 2, 3, 4, 5, 6. Okay? So that is how we number. If there's only one substituent, that's how we number. When there are two or more, we're going to identify the longest continuous carbon chain. So we're going to highlight it, which is here we can see. Then, once you identify, then that's going to be your root name, for example, like your last name. And then we can number based off of that. So once again, you're going to identify the substituents attached to the parent chain, which are these two. These are substituents. And then we're going to number the parent chain from the end so that the first substituent from either side is given the lowest possible number. If there are two or more groups and the numbering is a tie, the group that comes first alphabetically gets the lowest number. So in this situation, we have 2 on this side and 3 on this side. Okay? Based off of this, because there are 2 or more groups, and the numbering is kind of a tie, the group that comes first alphabetically gets the lowest number position. So we have to look at the substituent groups. Alphabetically, we have ethyl and we have methyl. Ethyl before methyl, alphabetically, E before M. So therefore, we have to number 1, 2, 3, 4, 5, 6, 7, 8. So we have to look at the substituent groups and then number accordingly. Okay, so ethyl is here. We have methyl here. Because E before M, that is how we number it. Now, naming. So if the substituent is present more than once, use a prefix to indicate this is di, tri, tetra, and include a number to indicate each substituent location. So that's why we number them. And then when writing the final name, we're going to list the substituents in alphabetical order, separate words and numbers with hyphens, and if the substituent is present more than once, separate all the numbers by comma. So always do this in alphabetical order, such as prefixes, di, tri, tetra, do not count in alphabetical order. It's actually the compound. And then prefixes such as cyclo and iso do not also count. So in this example here, we're going to re-highlight everything so we have it. This is our parent chain. We have our substituent groups. Now we have our numbers, 1, 2, 3, 4, 5, 6, 7, 8. Now based off of this, we have our ethyl and we have our methyl. We're going to number it and name it. So our ethyl is at 4, so then we're going to write 4 hyphen ethyl, because ethyl is at part 4. Then our methyl is at 6, so hyphen 6 hyphen methyl. But because there are 8 here, we write methyl octane because there's 8. Okay, so that is how we name our molecule. So it's really important to go back to that previous chart that had all of the naming. So we know if there's how many carbons, then we can name it based off of that. Here's another example. So once again, identify your substituents. Okay, once again, we have 2 methyls and then an ethyl. Just start, once again, on either side. So we're going to name 1, 2, 3, 4, 5, 6, 7, 8. Then we have our methyl, ethyl, and our methyl again. And then in this situation, we have 4. We have ethyl. And then because we have 2 methyls, we're going to do 2 and 7 di, because there's 2 methyl. And then because there's 8 carbons, octane. Okay. Pause now and try example 3 on your own. Okay, check your work. This one is going to be really, really tricky. So this is our substituent. This is butane, 241. Okay. In this situation here, we have our chlorine, which is chloro. And then we have our bromo. So therefore, if we were to number this, we have 1, 2, 3, write down 4, 5, 6, 7, 8, 9. And so therefore, this would be 7, bromo, because we're going in order, once again, alphabetically, 4, butan, oops, oh no, my pen died. So 4 butan, 241, 2 chlorononane. So I want you to try the next few examples out, and I will post the answers once my pencil has charged. All right, check your work here. Make sure you got this correct. And then I want you to try out the next 3 slides here of different examples. So draw out the following organic molecules. We'll do the first 2 together, and then the rest you will try it on your own. So we have 2,3-dimethylbutane. So this is di, which is 2. So that means we're going to write out CH3, CH, CH, CH3. Once again, it's on 2 and 3. So we'll have a methyl on 2 and 3. Okay. 2,2-dimethylbutane. Here again, because they're both on 2, we'll write CH3, C, because of how the bonds work, CH3, CH2, CH3. We need to make sure that when we bond here, our carbons have enough room to bond. So we can't have too many hydrogens. If we had a hydrogen here, it wouldn't work because it's too many bonds, okay?